Hello. Um, my name is Christian Favis, and this is my project for this is my project 3 for Aerofundies summer of 2026. Uh, Here we are. Here's the project. We will be doing just the second part, the fluent 2D flow over a stationary cylinder with a diameter of 1 meter for viscid, viscous laminar, and viscous turbulent cases. So we will be doing 3 cases. Um, we are allowed to adjust our velocity inlet or our air properties, depending on whichever one that we need for the required Reynolds number for the laminar and turbulent viscous flows. But for the viscid flow, we can take it as 5 meters per second, and then we get all of these um, from our results. So let's get started here. We grab a fluid and flow fluid work block, click on geometry. We're gonna have it's 2D analysis, right click, and then new design model geometry. We're just gonna wait for that to load. All right, here we are. We're gonna go into this looking at from the z-axis, the xy plane. We're gonna sketch, click sketching. We're going to make a circle. Again, sorry for my graphical issues because my computer is breaking down, but we will continue. We make a rectangle, and now we are going to dimension it. So we want also make sure units meters. Dimensions. We're going to make this diameter. Again, remember it's a cylinder of 1 meter. It's going to be very small, at least because we're zoomed out. So it's going to be 1 meter. And we're going to constrain. We want to make symmetry about the top and middle. So make sure you click the middle and then click the top and bottom parts of the rectangle. And then we're going to dimension the rectangle. We want it to be, for this, I'm going to make this 25 meters long. Oops, my bad. 25 meters. And then I'm going to make the height 12 meters high. So you see it's symmetrical about it. And then we want to do a horizontal dimension from the center, and we're just gonna make it 5. So we have a circle that we're going to that's going to be our cylinder, and we created our whole like domain for our flow, and the flow will be going from left to right, and you'll see different wake patterns or whatever behind it trailing. That's why we have it very long. So now we can just go to concept, surface and sketches. Click your sketch, the rectangular box, and then click generate. And then you should get something like this. Looks good. Make sure you save. But yeah, you can always just make sure you update it also in this block diagram right here, and then double click mesh so we can move on to the meshing. Just wait for it to load. Sometimes it takes a little while. All right, and here we are in the mesh. First thing first, so we don't forget, I'm gonna make our name sections. Click the top wall, hold Control, click the bottom wall, click N. We're gonna just title this walls. Click the inlet, title the inlet. Click outlet, click N. Title it outlet. Oops, outlet. Okay, and one more thing, click the around the cylinder, and you can just title it like cylinder or whatever, just so you know that this is the edge of the cylinder that we are going to be defining our flow around. So first things first, click on mesh. We're going to use an element size of 0.08 meters. Very small. Also, right click, then click method. We're going to have the geometry selection. This is going to be our method where for the whole around the whole surface, we're going to do triangles. That's what I found to be the best, well, most optimal for in terms of computing and how accurate it is. Next, we're going to have some sizing. And we are going to want the sizing around the cylinder. So switch to your edge, click the edge, click apply. It'll be edge sizing. We are going to have a number of divisions, and we are going to have that as 250 divisions. And we do not want to capture curvature, so click that to no. Yeah, no, and then we want the behavior to be hard. No bias, yes. All right. Now, one more thing. We want to have some inflation so we can capture what's accurately happening around the cylinder very closely to the edge. So click your body and then go to boundary. Make sure you click the cylinder, click apply. And we want first layer thickness instead. So, and you can decide what you want your mesh to be like based on your own parameters, but I'm going to use a first layer height of 0.01 meters. And we're gonna want quite a bit of layers, so we're going to go to 60, and that should be good. Right click mesh, click generate, and wait until the mesh generates. Your name selection should show up here: walls, inlet, outlet, cylinder, and it should highlight your corresponding walls. So we get something kind of crazy like this. You see a bunch of triangles, but if you look closer to the cylinder, you can see how it's more defined and more accurate, so you can get better better analysis and results around that. But here, that should be good. We have walls top and bottom, inlet, outlet, cylinder. All right, that's good. All right, so you can close that out. Right click mesh, make sure you update it. All right, and once that's done, you can double click setup. We are going to start our setup now. Double precision, and 2 solver processes, and then click start because that is what my computer will be able to handle, hopefully. And just wait for it to load up. All right. So we should get our mesh right here. And we will be doing all of these. For this first case, I'm gonna do the inviscid flow, and then we're gonna do viscous laminar, and then viscous turbulent cases. So we could take the inlet velocity as 5 meters per second for inviscid flow. All right. So first things first, you can keep everything here normal. We are going to change our viscous model to inviscid. Click OK. That should be good. Let's see here. Materials, fluid. We will be using air. I believe that's what it's specified in the project. But you can see here air. You can change the density if you want. It's not needed. Well, for this case that I'm doing, at least. Then we will go to our boundary conditions, go to inlet, and we are going to change it to 5 because that is for the inviscid case. Outlet, pressure outlet. Make sure it's 0 gauge pressure, and then check our wall. Cylinder walls. Just make sure that they're non-moving, they're stationary walls. I don't know why it's not showing up, but it should automatically be just walls stationary. Next, we're going to go to method. We are going to run a simple scheme with a presto pressure. Then go to the monitors, residuals. We're going to want them to converge, or at least try to converge. So I'm just going to add a couple zeros. And then we are going to initialize. Make sure the initialization runs. And we are going to run this for 800 iterations. You can do more, you can do less. It depends on your computer. But just calculate the process and it will start to run for 800 iterations. So just wait until that finishes. And our calculation completed. It actually finished before we needed to do that. So that's nice. All right. So now we can actually start. Excuse me. So here we are. We need to get our velocity contours with streamlines. So we are going to go to graphics. We are going to create a contour. So go to velocity, and then we can title it, or we title it velocity, and then we gotta get the contours of velocity, velocity magnitude, click all of that, save and display. Okay, so here's our velocity contour. Right now you can see that the velocity is coming in 5 meters per second, roughly. It's like that greenish color. Then it goes and then it stops, stagnation point. It drops to 0, 1.15 to e to the negative 0.1, or times 10 to the negative 1, sorry. And at the top, it looks like it reaches about 10 meters per second at the top going, give a roughly. So you can just take a picture of that. Well, you don't need, you need the velocity contour with the vectors as well for the streamlines. So just type in the streamlines. And then you just want the vectors of the velocity. Just click all of this, and then you can just save and display. It might take a minute. These are always the ones that take a little while. And you can, like, if you zoom in very closely, you can see that the arrows of the velocity and how it goes about. You can change the scale of the vectors too. You can change it to like 2, and you can also skip vectors to like open it up, like skip 1 to make there be less vectors, so it can be like a little bit more like visible on how it goes. You can see that there's a lot of vectors up here. Let's try skipping 3 instead and see how it looks. It's still very difficult because there's so much, but you can kind of see better how like the velocity changes about the stagnation points. You can see that it like comes to a 0, and then it goes up, and then goes down, and goes up. So that's good. All right. And then we can get that all on one by going to scene, get your velocity, get your streamlines, make your transparency something like that. Save and display. And then you can see the contours. You go in closer. Let's make this a little bit less transparent. Okay. You can see that the contours and how the streamlines along it change. Here we are. We gotta do. So that's our velocity contours with streamlines. One more thing, you can also get path lines if you want to analyze that as well. You can go to just path lines, and you can just color by velocity magnitude. Don't click all of them. You have to release from the inlet, and make your steps like 1,200 or 1,800. And then we can make it like line. Yeah, just keep it as line. And then we can just save and display, and you should see like nice path lines following the you can see how it goes around the cylinder, and there's like a stagnation line. And yeah, so that also works too. You can keep that in mind. This is your velocity path lines. So you can close that. Oops, I didn't say it, but it doesn't matter. Then if you want, you can use this to go save your picture. Save. Just click save. It's in file. Save picture. Now, let's move on to our pressure contours, which is the next case. It's easy as just going to contours. You can just title this pressure or whatever, and then cylinder. Click all of them. Pressure, static pressure. It's already defaulted. Then you see that. Makes sense in viscid flow. Most pressure, you have two stagnation points, one on the front, one on the back, and then it decreases over the top and bottom. So that's your static pressure. Here's your dynamic pressure. Looks right, it increases where the velocity increases as well at the top and bottom. And it decreases where velocity comes to a 0, which is a stagnation points behind it. Then we can go to total pressure. It should be remaining relatively constant. Yes, so as you can see here, it seems like a lot of different colors, but you can just tell that it is very close together, the numbers, and these are all just like numerical errors. So if you actually remove the auto range and type in your own range, you can see like from 10 to 17, and I save and display it, you can see that the total pressure remains roughly constant, and it's like very clear that in viscid flow that it's like actually doesn't change that much at all, and it's just the solver process, as you can see here by this color chart. But yes, that's for the contours. Total pressure, you can turn back auto range on. Next is plotting the velocity distribution on the surface of the cylinder for all cases. Okay, 1 second. We are going to go to the XY plot, I believe, for the velocity distribution. Yes. All right, so we just want the XY plot, and we want the velocity magnitude, and our surface is just going to be the cylinder. Direction vector, just keep the plot, it's going to be in the X direction because we have the flow going to the X direction, and just save the plot. As you can see here, here's our XY. This is our velocity about the cylinder. Goes 1 meters per second, or 1 times 10 to the 1, which is 10 meters per second. About 0 meters, which is the middle, because we have it at the origin and it's a 1 diameter, so 0.5 to negative 0.5, and it stops at 0 at the front, and goes to 0 at the back as well. So that checks out. Make sure you can write to file if you need the data, and export it to Excel, then put that on your report. Next, So that is the velocity distribution on the surface of the cylinder. Then we are wanting the CP distribution on the surface of the cylinder as well. So we will be making another XY plot. And you could just go to pressure. And we want the pressure coefficient again on the cylinder. I'm going to title this like pressure coef. All right, and then save plot. And this is kind of what we get. Ah, 1 second, one moment. Remember, before doing anything, at least calculating, we must go to reference values. And you see here that it is calculating from the wrong velocity. So we want to make sure that it's actually from the inlet, which is 5 meters per second. So go back to, where is this XY plot, our pressure coefficient, and we want to save the plot again. Now we get something that's more accurate to our results. We get a -3 at the bottom, and we get a 1 at the stagnation points, a CP of 1. Checks out with the theory. And we need like 1 CP for the whole, that's where the stagnation points are. So this graph accurately represents that. Again, make sure you export the data. Furthermore, next up, we need to get the drag coefficients for all cases. All right. So then lastly, to do everything, we do not go back to scene, sorry. We go to reports and we go to forces. Go to forces, just click cylinder, in your direction vector 1, forces 1, and we are going to print it. And you should see down here in the console, it prints our forces. And we have our cylinder, and your drag coefficient will be this number right here. And in inviscid flow, it is we get a 0.0009, which is a very close number to 0. It is a very low number, and you can, that makes sense because there is no viscous forces, meaning that there is no drag in inviscid flow. So it should be close to 0, and this is just some error that we get from like computing in the numbers in ANSYS and how we set up the simulation. But we get a number that's approximately 0, so we can just roughly assume it to be 0, which would make sense. The last part is to compare the wake patterns and drag coefficients with experimental data online. You will be doing this on your own, but if we go back to our scene, we can save and display it. There is no wake. There is no you can compare your drag coefficient with other things, but there is no wake. It's approximately symmetrical about this. But it will become more apparent in the next few simulations. So now we are going to be moving on to our viscous laminar case. So and then after that, we will move on to the turbulent. So we are going to change a couple things back in the process. I'm going to close this out. We are going to go to laminar, click OK, make sure the model's laminar. Yeah, and we're going to keep the air properties just like that. Yeah, we aren't going to change anything. Make sure when you're doing your process, you solve for the Reynolds number to make sure it's accurate over the cylinder, rho VD overview. This is your dynamic viscosity, not kinematic. Excuse me. So this, I'm going to keep track of those, but it should be air. Actually, did I? Okay. And we are going to change our inlet velocity instead to, I believe, after calculating it, we are going to do a very low number, 0.01467. Apply, close. make sure our outlet's the same. And just a quick thing, we're going to, let me show the velocity real quick. Remember how this is, we are going to compare it and contrast. So we're gonna go back. Let's change our reference values again because it actually doesn't reflect it yet. So we're gonna click walls, go back to inlet, and now our velocity is changed there. We're gonna keep the methods the same, simple, presto, yes. Residual, and we're just gonna go to initializations, click initialize. We're gonna run this process again, go to run calculations and click calculate. I'll just wait for that to calculate. All right, we're done back with our calculations complete, and I'm just gonna run through this really quickly. So we already have everything set up. We can just go to scene, save and display the velocity in the streamlines. And now you can see here, this is for our laminar case, that we actually get kind of a crazy, we get our stagnation point, but we see like a lot of swirling about in the wake. There's actually a wake now. And it's following it due to boundary layer actually occurring now. You can actually see that at the surface of the cylinder, it's changing a lot more. Or it's not changing a lot more, excuse me. It's actually going to zero at the surface, which is what we expected due to the no slip condition, and the cylinder is stationary, so it's not rotating whatsoever, so there should be no velocities. But in the wake region, you can see a lot of vorticities. It's actually going up and down and actually rotating and going back, and there's like a backflow, but it ends up kind of somewhat stabilizing near the end. But you can see the wake region, and you can use that to compare with experimental data you find online according to your Reynolds number for this test and more. So that is makes sense. So here's our pressure. This is going to be our total pressure. Sorry, it's still on auto our range that we made. So click back auto range, click the save and display. Shows your total range. Yeah, looks good. There's a drop in pressure behind it. It's low pressure, low velocity, makes sense. This is like a higher pressure. The most pressure is going to be right here. Well, not the most pressure, apologies. But it remains relatively constant, which makes sense. You can see that there's actually a boundary layer now on the walls at the top and bottom, but yes, that doesn't affect our cylinder because it's far away. But we can look at the dynamic pressure as well. You can see comes to a stagnation point, and then around the cylinder it's zero approximately, and then it's like due to the boundary layer there's low velocity behind it. It increases to the top, increases the most at the top, which we see, and our numbers are very small because of our velocity. But keep on going, go to static pressure, save and display. Here you are. And that's our static pressure. Seems right, most in the front. All right, that's good. Next, velocity distribution. So let me make sure. Did we change our reference values? Yes, okay, the reference values are changed. So we go to our XY plot. Save plot, this should be our velocity. Look at what we get, 0, no slip condition, makes sense. Next is the CP distribution. So around the cylinder, save plot, and we get something about like 1.5, 1.46. So that makes sense about the stagnation point, because now we are actually introducing some forces. So CP is like going to be a little bit higher than 1. So a lot of the viscous forces and frictional forces is acting on it, and you can see that it drops. This is 0, and there's this wake region that occurs, and it just kind of tapers out like this. So that's your CP distribution. Then one more time, we are going to go to forces, and we are going to calculate prints, and you get a drag of 1.381807. So that is your drag force, or coefficient of drag, excuse me, about the wall, about the cylinder. So that's for your laminar case. Let me check if I got everything. Velocity, pressure, distribution, the CP distribution, and drag coefficients. Yes. All right. And then again, you can go back to your velocity if you want to look at the wake pattern or whatever, and you can see how the vorticity is occurring. One more time, we are going to change, and we're going to finally finish this off with our K epsilon for our turbulent case. Let me change this to that real quick. We're going to change, we're not going to change our air, but we are going to change our inlet. Really easy. Since we just want to make it turbulent, we are going to make this just 15 meters per second. Apply, close, make sure our reference values change. Go back to inlet, should show 15. That's good. Initialize this. We don't need to change anything else. Go to run, and then click calculate. And just let that run one more time. All right, here's our calculations. We are completed. Once again, we are going to start with the, not this, sorry, the velocity contours. Save and display. And you can see that there's actually a much less of a wake region, but there's actually more rotation in the wake region. But because of the turbulent flow, there's a stagnation point. It actually just overall, excuse me, sorry. Because of the turbulent flow, the wake region is actually a lot less because of the mixing of the velocities due to the energy, and it's a lot more energized velocity. So you can see that. You can look at the velocities just by itself. shows you that it's 0 about it, and then you can see like the wake region, and it's actually a lot less than the laminar, which actually makes sense. Now we're gonna go to pressures, auto range, save and display. Here's our pressures. There's a stagnation point, and then there's actually a lot of static pressure back here, but that's because it's the wake region. Dynamic pressure, here it is. You can see stagnation point, and then there's low velocity back here. This is where the most dynamic pressure is, at the top and bottom. Then total pressure should be relatively the same. Yeah, stays constant, but then you see that wake region where there's just low pressure, low velocity, and it doesn't account for all the pressure, and it just, that's because of the wake region. So yep, that all checks out. Next is the velocity distribution. Using our knowledge, we know that we should get 0. Yep, and it shows 0 around the cylinder. That makes sense. Then we're gonna go get our pressure distribution, our pressure coefficient, save our plot. And this is what we get. We get 1 at the nose, and it goes down, 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 down until it finally goes back around and goes to 0 about the edge. So that's our pressure coefficient. And lastly, we get our drag forces. Go to forces, print, and we get something like this. A lot less than drag than laminar. So that's about it for this whole project that I can show. Make sure you go do everything else. So yes, thank you for watching. And have a good day. There's the velocity contours again. All right, thank you.